Good afternoon. This lecture we will be looking into MIPS logical instructions. There are three bitwise logical instructions which are AND, OR, NOR are the one we are going to discuss it now. The syntax for the AND. So the opcode is AND and then destination register and then source 1 register followed by source 2 register. Example, let's say AND register T0, comma register T1 and then register T2. So whatever the content of register T1 and the content of register T2 will be done with the bitwise AND operation. For example, before the AND, let's assume we assigned a value to register T1, let's say 2. And then register T2 is assigned with let's say the value 4. So the content of register T1 is 2. Basically it's written in binary in the computer memory. So I told you already every register is of 32 bits in MIPS because we are discussing MIPS 32-bit architecture. So that means the content of the registers will be 32 bits. Totally it will be having 32 bits. So register T1. So what will be the content? 2. 2 will be written in binary. So in 32 bits you will be having 2 like this. So 2 is 0010. Okay, in short, in the next exercises, we won't be writing the 32 bits. I will be writing only the required bits to be faster. As for the first exercise, I will be writing the content of the registers as a 32 bit. Okay, so here we have 32 bits of the content. Register T1, the value is 2. 2 is 10. Same, we have the register T2. Just now we assigned a value 4 to register T2. So 4 in the case, so you will be having 32 bits and 4 is 0100. So this is the content 4. Now and register T0, register T1, register T2. So we will be doing the bitwise and let's look into the topic. It's bitwise logical operations and or NOR. Okay, so when we do the bitwise, what will be the result of the destination register, which is T0? This is the destination register. So you will be doing the bitwise AND. You have to remember the truth table of AND, which is if the input is 0 and 0, output is 0. If any one of the input is 1, also the output is 0. If both the input are 1, then you will get a 1. So here 0, 0 will get a 0. And the next bit is 1, 0. So again, the next bit is also 0. The next bit also. So it goes like that, 32 bits. So what is the output? 0, by the way. So when you do the AND, it takes the content of the source 1 register, takes the content of the source 2 register and it does the bitwise AND. Bitwise AND means performs the AND operation from left to right, from the least significant bit to the most significant bit. LSB to MSB. So starting from the least significant bit, it compared with the least significant bit of the another source register and the AND operation is done. So the result is calculated. Then the next bit and then the next bit. It continues until the most significant bit. So this is bitwise AND. Same goes for the bitwise OR. So when you do the OR, the syntax is the same. You'll write the opcode R, you'll write the destination register and then source 1 register and then source 2 register. The same idea. Example, Let's look into the same example. You have register T1 loaded with the value 2. You have register T2 loaded with the value 4. So I'm doing the OR and the resultant register is, the destination register is register T0. So here we are doing the bitwise OR. OR means you have to remember the truth table again. If both the registers are 0, you will get a 0. Output is 0. If both the input is 0, the output is 0. If any one of the input is 1, you get a 1. Let's say 1, 0 or the 0 or 1 or both are 1, you get a 1. So this is the truth table of OR. So you have to remember the truth table. You already studied it in digital logic design. So let's continue with the same exercise. Register T1 contains 2, which is 0, 0, 1, 0. Register T1 contains, register T1 is 2, register T2 is 4, 0, 1, 0, 0. Basically, the content will be in 32 bits. To be faster, I'm writing only the 4 bits data. So the resultant register, the destination register. So again the bitwise OR starts from the least significant bit to the most significant bit. So let's see the least significant bit 0, 0, 0. And the next one 1, 0, 1. And the next bit 0, 1. And the next bit is 0. So it goes like that. So this is the result. So this is the bitwise and bitwise OR. The next one is, so our topic is bitwise and or NOR. And NOR is over. Now let's move on to the NOR. This is also a bitwise operation. Performance is done bit by bit. That is the meaning of bitwise. Okay, the operation is done bit by bit from the least significant bit to the most significant bit. So NOR means not OR. That is the meaning of NOR. So what are you going to do is, the inner operation of the NOR is, first it calculates the OR and then it reverses the bits. Not, you know the not already, it inverts the bits. 1 becomes 0, 0 becomes 1. Let's say the syntax, it's quite similar to the other bitwise operations. NOR, destination register, source 1 register, and then source 2 register. Same exercise, we will be looking into that. Let's say register T1 is loaded with 2, register T2 is loaded with 4. Now I'm going to do the NOR, the resultant. Let's keep register T0 as it is. As I mentioned, NOR means not OR. So you will get the output. What will be the output stored in the T0 is, MIPS will calculate the OR of these two registers. First it will do the OR and then it will do the NOT. That is the idea. So first it will do the OR and then it will do the NOT, and then that result will be stored here in this destination register. So here in this exercise, first source is having 2, second source is having 4. So what will be the result? Let's look into the operation. Register T1 contains 0, 2, 0, 0, 1, 0. Register T2 contains 4, which is 0, 1, 0, 0. So what will be the register T0? First we need the OR. The OR of these two is 0, 1, 1, 0. This is the result you got from OR. Now let's do the NOT. NOT means you invert the bits. So this is the OR of the register T1 and register T2. Now let's do the NOT. In NOT means 0 here becomes 1, 1 becomes 0, this one becomes 0 and this one becomes 1. By the way, we have 32 bits of zeros. So all those becomes 1, 1, 1, 1, 1, 1. Fine. So you will be writing 32 bits. So totally when you count the number of bits, you should get 32 bits. So this is the idea of NOR. Okay, the idea is the same. Bit by bit, we will be doing the logical operation starting from the least significant bit until the most significant bit, from here to here, okay, from your right to left, okay.